Speaker number one is our own Bob Siegfried. He is a graduate of Cornell in mechanical engineering, a registered professional engineer in Ohio and Washington State. Bob was employed by P&G for 43 years and was requested by our board to arrange this presentation. And as you can see, it's a popular presentation. Bob requested that all comments be held for the question period at the end of the program. So let's welcome Bob Siegfried.
Thank you, Gene. The nuclear business has started out with two strikes against it. It continues on with people worried about North Korea, India, Pakistan, Israel, Iran. It seems to have affected the thinking. There may be something else that's affecting the thinking when you talk about nuclear power. So I'm going to try to not use the word power today, and I'll try to talk about nuclear energy, because I think that's a little bit easier for people to accept and a lot more interesting for engineers, because we're deeply involved in energy in every aspect. The engineering of nuclear energy has continued even though the construction hasn't been great in this country for the last few years. The engineers have made progress. That's one of the things we're going to be talking about today with Wayne, and I'm going to mention a little bit about it because I got a news blurb about a nuclear plant that Toshiba is trying to give away to a little village in Alaska. Now, before I talk about the sources of nuclear energy, I want to mention two little personal histories that indicate how slow some of the world-shaking changes which happen, how slow they happen, and how they are resisted. In Helen's family, they had a home on Wheeler Street, which is just a couple blocks from UC. There was a stable behind the house for Helen's father's horse. He was a veterinarian and he needed private transportation. There were two other brothers living in the home with the grandfather and the grandmother and one granddaughter. The story I heard was that they talked about whether they ought to have a new house or a car, because they had no car. The decision was to build a house. They built a house on Ludlow Avenue. Happens to be about a block from where we are now. I mean, in our home. The problem was that when they came to have a garage, they'd located the house in such a way that the closest they could get this two-car garage was 216 feet from the back door and down about 20 feet of elevation, which was very inconvenient, but they can put up with it for about 100 years. The story with my own grandfather was very sad. He was a prominent engineer with Westinghouse. When his son left home to go to work, he bought a car. Grandfather was so upset with him buying a car that was about the last they saw of each other. The benefit for me was that as soon as I was working full-time, my dad helped me get into a car. So I'll show you that car.
1.5 horsepower.
These are some of the people that I was working with. It's hard to relate that to a nuclear power source. But the fact of the matter was that this car was so crude and so simple and so easy for people to understand that some of this philosophy has gone into the Toshiba project. One part in particular was the cooling requirements. People were familiar with steam coming from teapots, but not much else. And if you see steam coming out of a Model T Ford, you know you've got to stop that, or else you're going to burn the motor up. Technically, the coefficient of heat transfer between water and the heat source is very much higher than between steam and the heat source. So that when you see the steam, you've got to do something about it. In order to understand this principle, we were taught of the thermal siphon. Now, the thermal siphon is a process whereby a cool liquid, being more dense than a hot liquid, the cool liquid will push the hot liquid out of the heat zone and upward into the radiator or whatever you use to get rid of the heat. And this hot water then, on the same principle, is cooled, becomes heavy, and pushes down on the heated water in the heat zone and replaces it, and that water continues on to the top and is recirculated. So the system is completely open. No pumps, no valves, no thermostat, no temperature gauge, nothing. There was a similar situation with the lubrication. The process that the squeaky wheel gets the grease is no longer sufficient. You needed a liquid coolant to keep everything lubricated. Now this lubricant went in a sump. The connecting rods and other part of the engine dipped down into the sump if you kept the level high enough. The splash of these motor parts would carry oil to all the parts of the engine and the transmission. The transmission was always engaged. There was no shifting of gears. It was 20 years before shifting gears became so popular that the Model T became obsolete. Shifting of gears continued on pretty commonly until the 60s or 70s. I don't see George Gore here, but last time I rode in his Mercedes, he was still shifting gears. Now, the nuclear source has been offered to the state of Alaska while Sarah Palin was governor. She approved of this construction. Toshiba went ahead and made an application to the Nuclear Regulatory Agency. The plan was to put this nuclear source of energy into a city by the name of Galena, a city of about 700 people located on the Yukon River close to the Arctic Circle. These people, in the winter period when they only have 4 hours of daylight, when they're paying 47 cents a kilowatt hour for electric energy, they don't have much to do. At 47 cents a kilowatt hour, you really can't afford to have sewing industry or almost any other constructive activity other than the every other year dog sled races around the river. The power plant being offered by Toshiba on the right-hand side, this is the reactor, about 6 feet long and 18 inches in diameter. Looks very much like the water heater in the basement of your home. This was mentioned by David Sukarno, who's a Russian immigrant who developed RCA, the radios and the radio network and eventually the TV and the TV network. Now, Sukarno liked to be called General Sukarno because of his service during World War II. And General Sukarno's prediction was that by 1990, we would all have a nuclear power source in our basement. Well, instead we have computers in our basement and Blackberries in our pocket. So it shows that we can quickly adapt some things, but we didn't quickly adapt the nuclear reactor in the basement. The nuclear reactor is placed in a bored hole in the ground about 100 feet deep. The reason for this is one of those engineering problems like cooling and lubrication. That's the radioactivity. Now, radioactivity occurs naturally. When I brought this up to the board, I wondered how many of the board were familiar with the natural radioactivity in a crystal of galena, which was a part of what we played with as boys as a crystal radio. It turned out all the board was familiar with that. That surprised me. Anyway, the way you find this radioactivity in the crystal of galena is to go over the system, go over the crystal with a cat's whisker. You were wearing earphones, and you would know you found the area of radioactivity when you could hear a radio station on your earphones. The young people today call these pods, but they're the same thing. Earphones and pods are the same thing. The radioactivity in the nuclear reactor is a byproduct of the reaction. What is happening is that we're converting matter into energy, and it takes a very, very small amount of matter to make a tremendous amount of energy. The matter in this case is an isotope of uranium. The location of this reaction is, assume we start at the bottom, it slowly moves up the whole 6 feet or 2 meters, and all this time, day and night, 24/7, it's generating heat in a quantity of 10 megawatts. This reaction continues until all of the matter is used up. On this 6-foot device, it's used up in about 30 years. All during this time, you're making that amount of energy. At the end of 30 years, you can either pull this thing out of the hole and recycle it, or you can fill up the hole, dig another 2-foot hole down 100 feet. No big deal. In order to get the heat to the surface, you use sodium instead of water. Now, sodium is a common liquid metal which doesn't boil, and it does exhibit the properties required for this thermal siphon principle. This mercury is very hot. It's 1,032 degrees Fahrenheit. I can't quite describe how hot that really is, but it opens with that temperature all sorts of opportunities for mechanical and chemical processes. In its simplest form, it would go into a boiler to make steam. The steam could be used in earth-moving equipment or heating, electricity, many, many, many uses for steam from boilers. In addition, can make heated air. This heated air can be put into a jet engine. There are processes to use this temperature to directly produce hydrogen, which gives you the opportunity to feed fuel cells. The hydrogen, you don't need it for anything else, or don't need the power or the energy for anything else. This can be stored so that you have the ability of storing energy. All these things are very useful when you want to put people to work. And what the work is will depend on what the locality is. Now, in the city of Galena, one of the logical things is to refine the mineral galena and make lead. But whatever else, it's giving people jobs and work in an area isolated from everything else. This problem of isolation affects the people in the United States very strongly because of transmission losses for the electricity produced in the power plants. Now, transmission losses in this country amount to about 15% of the output of the power plant. That's true whether it's a hydroelectric plant or any other plant. Just getting the electricity through the copper wires causes the wires to heat up, the power is lost. And this goes all the way from the power plant to the alarm clock on the bedside table. These losses are very significant. 15% of all the power plants in the country is a lot of electricity. which is saved by having many small sources of energy over areas where it's distributed or where it can be used. Another advantage of a small energy source is to simply put these energy sources in a bundle so that you have multiples of 10, say 10 would give you 100 megawatts, which is a fair-sized unit. In contrast with the economies of size, you've got economies of scale, which we take advantage of by putting in very large power plants, energy plants. These plants are so expensive to engineer and build that the only way that we can justify them is to make them very, very large. A plant like this is maybe 3 times 1,600 kilowatts. Turn the program over to Wayne Laib, who has been asked to talk to us by the American Nuclear Society. Wayne has been working in the nuclear energy field for 40 years. He now works for Curtiss Wright Flow Control Company out in Anderson Township. I'm pleased and honored to introduce to you Mr. Wayne Laib.
We tailored this program. My first shot at a title was a nuclear renaissance. That's the term that gets thrown around the industry now with us coming out of the doldrums of the 70s and the 80s. And Bob suggested, with this being a local audience and people who may or may not have had connection to it, that we tie it locally. And to those of you who may not know, we have started life as a nuclear plant up the river. It's now a 1,300 megawatt, what we in the nuclear world refer to as a dirt burner, burning coal. I worked there during the construction. Never worked there as an operating plant. We want to tie this to where we were then and where we are now. The plant as it was, that picture was actually taken in probably 77, 78 when I was working there. One of my fellow employees rented an airplane, went up and took a picture. And you see what we have down below. It's quite a mess. As a matter of fact, this little part here is what would have been there had it stayed a nuke. Everything else you see is there for one purpose and one purpose only, and that's to burn coal. And that kind of factors into the whole thing about waste, which is something I'll touch on a little bit later. Everybody got to see the maps that were passed around at lunch. If you transpose that onto this map, this is a map of all of the plants to date that are in the early stages of getting new units. They're in the licensing process. With the exception of the Victory County station in Texas, and there's one other, the William Lee County in North Carolina, they are all to be sited on existing power plant sites. Virtually every plant that's in operation today began life with the intention that it have more units than what actually came up out of the ground and went online. So the infrastructure is there in a lot of respects, and the environmental impact statements have been done and all that sort of thing, and they're accepted by the people in their communities. Things that have changed to get us to this point. We had a little discussion at lunch about this, a little bit of definitions. You'll hear things referred to the certification and approval process. What we now have in front of the NRC is the GEs, the Westinghouses, the Toshibas, the Arevas of the world have developed plant designs, and presented them to the NRC. They're in the review and approval process, and once those things are approved by the NRC, anybody who wants one can buy that design, and it's licensed. It's ready to go. You have an early siting permit, which allows utilities to go in and move dirt in ancillary structures, in infrastructure removed from the nuclear island to get started on things that aren't nuclear related, but to prepare for the site, for the plant to be constructed. And then most importantly is a COL, the Combined Operating License. In the old days, if I wanted to build a power plant, I went to the NRC and I asked for permission to start construction. And they said, okay, do your groundwork. So you went in and you did your environmental impact. You presented that to the NRC, and they said, yeah, this is suitable for that type of thing. Then you applied for a construction permit. They did their thing, and they said, okay, here's your construction permit. The plant design had to be presented to them. There are 105 operating nuclear power plants in this country right now, and they're all pretty much customized. There's not a lot of similarity from one to another, even though they're the same type or manufactured by the same NSSS supplier. Once you went through all that, you went to the NRC and said, okay, I'd like to load fuel. So they let you load fuel. You're allowed to take the reactor up to 5% power, check everything out, make sure it works, everything's wonderful. You get to that point, then you go back and say, okay, I want to run this and make some money. They give you your operating license and away you go. Problem is at any stop of the way, you could be stopped. And that happened at a place called Shoreham on Long Island. They built a power plant up there. They went through all these steps, got to the very last one, and the local municipalities refused to participate in the emergency response plan, and as a result, they never got their operating license. And today, that plant site is a greenfield. They completely tore it down, ripped it up, threw it away. The Combined Operating License says, if you build one of these approved designs on our approved site, and you build it the way it's designed to be built, you will receive your operating license. So when you sign up for it at the beginning, you know you're going to be able to run that plant, and it's not a gamble, it's not a crapshoot that you're making with your shareholders' money. And that's really the big thing that's different today from back in that time frame. That's what's different. The streamlined licensing process. You go through it, you know at the end if you do what you're supposed to do, you're going to get an operating license. The standard plant designs. You buy a GE ESBWR, you buy a Westinghouse Ap1000, you buy one of Areva's EPRs, you build it the way they say you build it and is approved, bam, you get a license. Shorter construction periods. There's a lot of modular and prefab construction that is designed into these plants that should speed things up. Enhanced safety. Bob alluded to this in his talk. The current fleet of nuclear units, it's all active. You have to have power to open a valve. You have to have power to turn on a pump. You have to have operator interaction. You have to have a diesel generator there to provide power if the grid dies on you. That has been lessened considerably, and we're relying on natural convection, gravity, the forces of nature that can take care of the plant without any operator or any active actions. Passive safety systems, and then of course the public acceptance. It's a different ballgame. When you have the co-founder of Greenpeace, Dr. Patrick Moore, stand in front of the world and say, I was wrong about nuclear power. We made a mistake by tying nuclear energy to nuclear weapons. They need to be separated. We did this country a great disservice by doing that, and that is starting to creep into our society. Just as a general look at one of the pre-approved designs, the Westinghouse Ap1000. I'm not going to get into a lot of nuts and bolts, though. As Lee said, I could talk for hours. I promised I wouldn't. The Ap1000 is actually under construction right now. There's a site near Savannah, Georgia. The Vogel site has 2 operating units on it. They are doing their early site work now. They